I am Lauren Nagel from the University of Michigan. I'm going to introduce our single-shot double pulse technique to determine the detonation energy in nanosecond ablation plasma plume formation. Interest in the physics of pulse laser ablation for solid samples has grown with the need to optimize its applications, such as laser processing and material analysis, like the works of Dyer and Weiss. It's the absorbed laser energy that is a significant contributor to the dynamics of laser ablation plume formation and contributes to the formation of what we see as an induced shockwave. These induced shockwaves carry a significant amount of information regarding the processes occurring during laser ablation, as studied by Kness and Gordon. The time evolution and geometry of these induced shockwaves are defined by the energy of the laser pulse and the shape of the generated plasma. This relationship of the shock wave and deposited energy motivates a need for characterization of these shock waves with improved fidelity, specifically of their spatial and temporal resolution. Pulse laser ablation of solid samples is used to investigate and monitor special nuclear material. For example, FINCO simulates nuclear fireball chemistries at the time of debris condensation, and FINI utilizes multi-filament ablation of solid targets as a mechanism to guide spectroscopic signals over long-range distances. Both of these projects required an optimized understanding of the laser energy deposited. It is the Setov-Taylor blast model that can be applied to laser-induced plasma to describe the evolution of the induced shock, both spatially and temporally. As seen in the equation here, it relates the time and energy to the expansion radius. The laser energy deposited on a target can estimate the energy attributed to plume formation if this equation is rearranged. This energy is usually calculated by measuring the shock dimension at several delays by means of scanning the delay of a probe laser with respect to the ablation laser. This method, however, assumes the shock wave of different laser shots at the variable delays are equivalent to a single laser shot measured at the same delays. When this cannot be assumed, which is when the plasma cannot be consistently replicated, for example, when laser parameters, target conditions, or the ambient condition are not able to remain constant, then a single measurement method would be preferred. We employ a single shot measurement by using a double pulse probe laser to image the shock wave at 2 delays, then fit the 2 measured shock dimensions with the blast model. Our setup can be seen here with our aluminum target, a mirror, our focusing lens for the ablation laser, an imaging lens, and a thin film polarizer, which was used to split the 2 cross-polarized probe beams from the double pulse laser. A typical shadowgraph of the shockwave measured at different delays is shown here for 2 different samples of various geometries. Our single-shot double pulse technique yields 2 measurements, which the Setov-Taylor blast model can be applied. Examples of these are shown on the bottom here. All shadowgraphs were analyzed in MATLAB by subtracting a background shot and then binarizing the image so that shockwave measurements could be automated. An example of selected shocks is shown here as well as under our technical approach. To validate our method, we compare the measured detonation energies from our single-shot double pulse technique to those measured using the more common scanning technique. 2 examples for different geometries of the scanning measurement are shown here. We find that the single-shot double pulse method shows good agreement to the scanning method. We also perform a parameter scan to determine the combination of probe beam delays that would yield the most consistent result with the typical scanning measurement. In future work, we plan to further determine the validity of the technique for other pulse geometries, such as planar and cylindrical, with an ultimate goal to implement the technique into a comprehensive experiment in which we study the multifilament ablation of solid targets. In previous work by this group, we found that multifilamentation may lead to the formation of numerous detonation sites on the target surface. Conventional methods to determine the energy deposited are unable to provide the resolution to distinguish between these detonation sites. However, our double pulse single shot method would. Thank you for attending my poster presentation.